Hello and welcome back to The Effect. In this video, we're going to be talking about a method for performing partial identification in a regression context. So you're running a regression, you want to know the effect of one thing on another. And in particular, the assumption that we are looking at is the assumption that we have controlled for all of the things we need to control for. We have identified all of the backdoor paths between our treatment and our outcome. And we have added control variables to account for all of those potential backdoor paths, meaning that if we've done this properly, we have identified the effect of our treatment on our outcome. Now, of course, there is a problem. It's very hard to convincingly say that you can actually control for every single backdoor path that you need to. Either you've probably forgotten some backdoor path that you weren't aware of, or you found one, but you couldn't really convincingly measure it all the way, and so there's something left. Right? We know that there's going to be something left when we control for these things, and so we're going to have a slight bias in our estimates. Partial identification comes to the rescue and says, yes, I know that you have some bias left in your estimates, but that doesn't mean that you have to give up and go home. Instead, you can just make the weaker assumption. Instead of having to assume that you have completely controlled for every single backdoor path and shut it all down, we'll just say that we've controlled for a lot of it. And we will consider the fact that there's some of it left, and we'll ask, well, how much of it might there be left? And if there is some of it left, how will that affect our estimate? That's what we're going to do in this video using a method from Cinelli and Hazlett in 2020, which is a common and increasingly popular way of thinking about partial identification in a regression model context. So what are we going to do with this? So the nice thing about regression and omitted variable bias, which is what we basically say when we have some backdoor that's open and there's a variable on that backdoor that we have not properly controlled for, meaning that we have some bias left in our estimate because we have not completely controlled for everything. Right? That's omitted variable bias. Now, the nice thing about omitted variable bias is that we know exactly how big it is. If we write out the formula for a regression analysis, we actually know exactly how big the bias is. It's this term over here on the right. And it's basically a combination of a few things. It's a combination of, if we have this omitted variable z that should be controlled for but isn't, it's the effect of z on the outcome variable, which is beta 2 here, mixed with the relationship between z and the x, the treatment variable that we're interested in. So basically, how strongly related is the omitted variable to the outcome times how strongly related is the omitted variable to the treatment variable. And then in the denominator, we have the variance of x. So those are basically the things that matter. The amount of bias we're going to get has to do with how strongly related our omitted variable is to the outcome and how strongly related it is to the treatment. So the fact that we know how big the bias is, why can't we just remove it? Well, the problem is that we can't actually estimate either of these things because we don't have data on z. That's sort of the point. It's an omitted variable. We don't have data on it. So what can we do then? Well, we can't necessarily estimate beta 2 or the covariation between x and z, but what we can do is say, well, let's think of some reasonable ranges for what those two values might be. And if we have reasonable ranges, then we can bound how large we think the bias might be. I'm not going to be able to tell you exactly how large the bias might be. If I could, then we could identify the estimate by just subtracting that bias out. But I can tell you, I think the bias is probably going to be in this range or less than this amount. And this will allow me to give you a range of plausible estimates. If I think that the bias is 0, then here's my estimate. If I think that it's somewhere between 0 and this value, then I can give you a range of estimates, which is more informative than either giving up and going home or assuming more than I really can assume and telling you that I have the actual right answer. So how does Cinelli and Hazlett take this idea and run with it? Well, they work with what are called partial R-squared values. We've talked briefly in previous videos about R-squared, which is the share of variation in an outcome variable that is statistically explained by the predictors. So if I can use a set of predictor variables, and using those set of predictor variables, I can predict, let's say 50% of the variation in my outcome, then I get an R-squared roughly of 0.5. Now, a partial R-squared value takes it a step further. It says, okay, I've got this set of variables. I'm going to predict my outcome with that, and then I'll subtract that prediction out. And then I have this second set of variables, and I'm going to predict what's left over, the residual, with that second set of variables. The R-squared from that second analysis, that's our partial R-squared. It's the R-squared of how our usually treatment variable explains the outcome after we've removed everything that's explained with our other predictor. Right? That's what's partial about it. It's only taking part of the explained variation, the part that we get after removing our covariance. So we have this idea of working with partial R-squared values. And what it turns out that you can do is by looking at a range of plausible partial R-squared values, you can get a range of estimates. You can say that I think the partial R-squared of the potential emitted variable and our outcome is between 0 and 0.3, just to make up some numbers. Or the partial R-squared of our emitted variable, which again, we can't observe, and our treatment variable is in this range between 0 and 0.4. And based on those possible ranges, I can combine them together based on this equation again to tell you exactly what the bias would be if those were the partial R-squared values. So I get a range of partial R-squared values, I combine them and calculate out exactly what the bias would be if those were in fact the true partial R-squared values. And that tells me what the debiased estimate would be. So I'm assuming a range of plausible R-squared values. From those assumptions, I'm going to calculate out the exact amount of bias that I would get if the R-squared was actually that value. I will subtract that bias out, and I will tell you what the debiased estimate would be if, in fact, the partial R-squared values were that level. In other words, if, in fact, we had some emitted variable that was a certain strength of predictor, how much would that mess our estimates up? Right? That's what we're going to do. So let's take Cinelli and Hazlett for a ride. We're going to use as an example study this 2020 study by Pena, Sanchez, and Harris that looked at imprisonment in response to crimes in the United Kingdom. What they were looking at was whether there was a gender disparity in lockup rate. So basically, if you are accused of a certain crime, what is the chance that you end up actually going to jail for that crime? And they're interested if gender has a causal effect on the rate of imprisonment. So in addition to regressing imprisonment on gender, they also had a bunch of control variables. They had 43 control variables for a bunch of different stuff. Stuff like, your socioeconomic background, previous convictions, whether you have a kid at home that you are responsible for caring for, or they're controlling for all of that stuff. And they found that there was an effect. They found that men were more likely to be sentenced to prison for the same crime as a woman after you control for all of these things. Now, granted, there are, of course, a bunch of other things that might need to be in that control variable list that are not in the control variable list. And so we have to ask ourselves, well, is this a robust result? If I assume that there is, in fact, some other control variable out there that I should have included, but didn't, either because I didn't measure it or didn't know about it, would our result go away? So our default estimate is 0.13, that for the particular set of crimes that we are looking at, men are 13 percentage points more likely to go to prison than women for the same crime with the same set of control variables. However, then we're going to take another step and we're going to say, what if there are some control variables we left out? And the way that we're going to approach this is this, right? I said that we need to take a range of reasonable R-squared, partial R-squared values, but what is reasonable? Well, we're going to use as benchmarks the other control variables that we already have in the data. We can ask ourselves something like this. Well, I know that the kind of drug that you might have been caught with might have an impact on, whether you get sentenced. And it might also be related to gender in some way. And so I can ask myself, well, if there was some other variable out there that was as strong of a confounder as the type of drug that you did, would that mess things up? And I can do that because I have data on what drug you did. And so I know how much bias was removed by adding that control variable. So I can ask myself, basically, what happens if I have another variable that explains as much as that? If I add that in, would that get rid of things? And that's where this graph comes in. So what this graph is doing is it's showing if we have other sets of control variables that are as strong as the ones that I'm showing you here, would we get rid of that effect? Would that 0.13 effect go to 0, for example? So over there on the left, you can see 1x drug class. And what that's showing is that drug class, the kind of drug that you were caught with, or the severity of drug that you were caught with, doesn't actually explain much of the treatment. Remember, treatment here is a certain gender. There wasn't a lot of variation in the class of drug that you were caught with across gender. So it doesn't really explain that much of the treatment, which means that it's probably not going to explain that much bias either. Right? So if we have another variable like this that doesn't really vary that much across gender, it's not going to give us that much bias because if you remember back to our equation, part of the bias is a combination of how much the emitted variable is related to the treatment and how related it is to the outcome. If it's not really related to the treatment, it doesn't remove that much bias. It is, however, fairly strongly related to the possibility of going to jail. So if we have another variable that was like this, a emitted variable that we don't include that is 1 time as strong as the drug class variable, then we see a change in our result. Our result in particular goes from 0.13 to 0.08, meaning that if we did have another emitted variable that was of similar importance to the type of drug that you had, or the severity of drug that you had, it would reduce our estimate, but it would not take us all the way to zero. It would not eliminate the gender bias finding that we have. Now, of course, you can go further with this. I also have on here, what if we had another whole set of variables that explained as much as the entire set of 43 confounders that we already controlled for? Now, if we do that, then indeed the entire effect does go away. We get to a effect that crosses that dashed line there. That dashed line is 0. The fact that we cross it means that if we did have a set of confounders that was as strong as those, it would in fact eliminate all of our effect and flip the sign of it potentially to go in the other direction. So then the question is not, which of these is right. It's how many assumptions are you willing to make? Are you willing to assume that we at least don't have another set of things we're missing that's as strong as all the stuff we already included, right? Like, socioeconomic status, the type of drug that you're in there for, whether you have kids at home. Those are all pretty important things, right? It seems unlikely to me that we have left out stuff that is as important as all of those things combined, right? Whether that's actually plausible to you is something you can think about and argue for in your research. Now, is there something that we've left out that's as strong as the severity of the drug? Maybe I could believe that, but it seems like if that is the case, that's not enough to get rid of our result. So what this graph is showing us is that our result is robust to certain kinds of things being omitted, but not everything, which makes sense. And then the question is, what's the amount of assumptions that we are willing to make, right? Do we think that it is plausible that we have some omitted variable that's as strong as drug class? Maybe. I think that's reasonable. Do we think there's something that's as strong as everything? Probably not. But again, that's the whole thing about partial identification. You don't have to choose an assumption that allows you to point identify a result. You can ask what assumptions do we think are actually reasonable and how far can we get with those assumptions. We can look at this in a different way. Instead of asking how strong are potential omitted confounders relative to the ones we already have, you can also ask, well, what if there was something out there that fully explained the outcome, right? Something that fully explained the outcome. We know that something determines whether you go to jail or not among people who are up for going to jail or they're in trial. So what if we happened to know all of that? If we could perfectly determine whether somebody was going to go to jail or not? Well, there's something out there. We don't know what it is, but let's imagine that we do have it. How strongly related to the treatment variable would it need to be to eliminate a result? And that's what this graph is about. It's an extreme value analysis. And you can see that it dips below the 0 line pretty quickly. This is saying that if we did have something that explained all of why you go to prison, it would only need to have a slight gender difference in order to fully explain away our result. Now, again, that said, you have to think about what's a reasonable assumption here. Of course, there's something out there that explains why people go to prison or not after they've been accused of a crime and they go to trial. Is there really a gender bias in those things after we've already controlled for all the stuff we've already controlled for? Maybe it's reasonable to say that that would indeed be below 0.01. I'm not sure. But these are two different ways of asking the question, what is a reasonable amount of partial R squared to assume? Because we just need to bound that in some way. And once you do have an idea of what that range is, you can say exactly what range of plausible estimates you can back and say that I do believe this is true because I believe the assumptions that went into it. So that is the approach that we are taking to how we can implement partial identification in a regression context. I think this is a very valuable and powerful approach that allows you to say things much more accurately without having to walk away from analyses just because you can't do a quasi-experimental study. That's it. Thank you very much. I'll see you in the next video.